Oh, Liz, are you going to EMNLP finally?
I turns out I'm going to, which is insane. I did not expect that. We
Nice.
officially were told we could 2 weeks ago, and so it seems like there's going to be uh, a small, like, I don't know. I think I might see more people from my department in person at once at EMNLP than I have in the last couple of months here. But yeah, crazy. So yeah,
Exciting.
I'm like very excited, but I'm also very unsure how many people will actually be there and what the hybrid situation will be. Are you going as well, or any? Okay, cool. I will see you in
Amazing.
person soon. Oh man, yeah. Uh, it'll also be funny. That'll be the first time I've seen Yanai in person since we started this. But yeah, hopefully it'll be fun, and I'll see you all in Gather Town if nothing else. So
Yeah, tell me, I'm really curious about how the hybrid conference will be, and it will be useful to know if if there are some like pain points that will be helpful for organizing NACL and things like that.
yeah, totally.
So tell me if something doesn't work.
We can have an official Zoom recap afterwards. And yes, I am drinking coffee with a straw. Hides my mug.
Mm, okay, I think we can start.
Um,
Um, sorry, Maria, go ahead.
no, go ahead. Sorry.
I was just saying, yeah, so hello everyone. Welcome to another edition of NLP with Friends. We are super happy to have Maria Ryskina join us today, who is an awesome PhD student at the Language Technologies Institute, Carnegie Mellon University. And Maria has kindly agreed to take questions during the talk, so feel free to raise your hand in Zoom or unmute yourself and ask clarification questions. We'll also be taking questions at the end. And I'll post the Dory link in the chat, but you can also just unmute yourself and ask at the end. Yeah, so I think that's it, and I'll hand it over to Maria.
Thank you, Abhilasha. So yes, my name is Maria. I'm a student at CMU LTI. I'm really happy to be here. I work on different creative phenomena in non-standard language. My talk today is about informal romanization. And as Abhilasha said, I will be taking questions during the talk, but I can't unfortunately see the chat when I'm sharing my screen. So if the organizers could monitor the questions, or just someone can unmute and interrupt me, that's okay too. And I will be giving examples from some languages that I do not speak. And I know that there are people in the audience who know much more about those languages than I do. So please, if I make any mistakes in there, please feel free to correct me. Okay, I'm going to start now. So first, I wanted to give you some context on this broader line of research. So we want our NLP systems to work on a variety of domains and genres, and ideally we want the same NLP system to work with, both news and social media. And many domains like social media or like fiction are likely to contain linguistic innovation, which could be new word forms like brony, new morphemes or morphological derivatives like pro-lifeness, or non-standard spellings like the spelling of tonight. And people can often infer the meanings of such non-standard items from their context and from the form itself, even if they haven't seen them before. But NLP systems usually discard this kind of linguistic innovation as noise. So the question is, can we encode the same kind of reasoning into our NLP systems so that it doesn't discard these fundamentally non-random phenomena as if they are data corruption? So before I formally introduce what informal romanization is, I'm going to give some real life examples of what inspired me to work on this problem. So let's say I'm messaging two of my friends. They both speak Russian, but live outside of Russia. And both of them are typing on their computers using their default keyboard layout. in this case, English and German, but they aren't actually writing in English or in German. They're writing in Russian. And I, as a Russian speaker, can understand what they're saying. And I can also tell that they actually said the same thing, even though what they typed is different. So I got curious about this variation. So if different people can encode the same words in different ways, what exactly makes it understandable for another Russian speaker, and what are the limits of this variation? And in the spirit of NLP with friends, here's one more example, this time directly from my chat history with Abhilasha, who's hosting this talk. And here you can see that there can even be variation within how the same person romanizes the same word. So there's really all kind of creativity and variation going on. All right, so let me define now what informal romanization is. And romanization means rendering non-Latin script languages using Latin alphabet. And I call it informal because it's used mostly in informal online communication, like chats. And people use it to get around Unicode issues like incorrect rendering, or when typing in native characters is complicated, like my friends who don't have a Cyrillic keyboard. And this kind of romanization is not standardized, so character substitution choices are up to the user. And that's why for each word in the table here, I'm showing multiple possible romanizations. So the substitutions vary, but they're not arbitrary. Most of them are based on phonetic or visual similarity between characters. In the examples here, I highlighted some phonetic substitutions in blue and some visual ones in red. But what does it really mean for two characters to be phonetically similar if each character can be pronounced many different ways? Like the letter G in English can be pronounced G or J or J. And that's just in English. I'm not counting any other Latin script language. What people do most often is they associate characters out of context through some kind of most prototypical phoneme for a character. So this illustration is courtesy of my advisor, Matt Gormley, who pointed out to me that we use a similar principle in language learning. So this is an educational toy that sings a song listing the most prototypical sound for every character. Like here it says A, and at the end of the song, it lists other possible pronunciations. So I'm not sure what makes A more prototypical than A. I don't know how speakers come up with these associations, so it's not really clear how one would formalize something like that. And the other type of phonetic substitution is based on phonetic realization in context. So here we have two Arabic words where the same character aleph is pronounced e or a. I hope I'm not egregiously mispronouncing it. And it's romanized as e or a respectively. So the visual similarity is based on glyph shapes. Glyphs are symbols that we use to express the character in writing. So here, two characters in different alphabets are considered similar if they are expressed by the same glyph or by similar looking glyphs. And a single non-Latin character can be represented by 2 or 3 consecutive characters in its romanization. Visual similarity is even more complex than this. It can be conditioned on a transformation, like Arabic ayin looks like a mirrored digit 3, so it's often substituted by 3. And it can be applied to a part of the glyph. Like here, the top part of the glyph, Hamza, kind of looks like a mirrored 2. So sometimes the whole character is represented by a 2. One structural constraint on the romanization process is that the character alignment is monotonic because you want to preserve the order of the characters. But the nature of the alignment depends on the type of writing system that the language uses. So the languages that are written using alphabets map to their romanized versions mostly one-to-one. Abjads, systems where characters mostly represent consonants. They often would not have vowels written in the native script, but they would be written explicitly in the romanization. So here the alignments are again mostly one-to-one, but with a lot of null alignments for such omitted vowels. And abugidas, these are the kind of writing systems used by many South Asian languages, are mostly one-to-many. You can see that each symbol here represents a syllable, but we're not actually working with those symbols directly. We're working with their Unicode representations because that's what we have in our computers. And if you look at the underlying Unicode code points, you'll see that many of those symbols are compositional. So it's actually one-to-one mixed with one-to-many. So the task I'm going to focus on in this talk is converting the Romanized text into the conventional orthography of the language. We observe the Romanized text, or what the user typed, and we want to reconstruct what they meant, or the native script text. We experimented with 3 languages here: Russian, Egyptian, Arabic, and Kannada. They're all from different families, all written in different scripts, and all those scripts belong to different classes of writing systems. As I said, people use informal romanization when typing in native script is inconvenient. So there isn't really going to be naturally occurring parallel data for this task. So we're going to use an unsupervised approach that doesn't require parallel training data. As I've shown before, people usually substitute characters with ones that are phonetically or visually similar. And we've observed people use the same principles of similarity across multiple languages, although of course to a different extent. So our hypothesis is that if we encode these shared notions of similarity into our model as inductive bias, then this inductive bias can somewhat compensate for the lack of parallel annotated data. And to create this inductive bias, we're going to use human curated resources that were built manually and that use the same principle of similarity. Did that make sense so far? Any questions? Okay. So we're going to take a decipherment approach to this task, which means we'll be treating romanization as if it's a substitution cipher. So we'll think of it as if the native script input was passed through a noisy channel and came out encoded in Latin alphabet. Our goal is to reconstruct the plain text from the observed ciphertext. So this is the mathematical formalization of our noisy channel model. The likelihood of the Romanized sequence decomposes into the transition probability, emission probability, and the prior and the emission parameters. And because we don't actually know the correct native script sequence, we're going to marginalize over all possible ones. And apologies for the awkward notation here. N is not an index. N is the value of the latent native script sequence. The emission probability should also decompose by character, but for that we need to know which latent character produced which observed one. Or in other words, we need to know the latent alignment. So we are actually marginalizing not just over all possible latent sequences, but also over all possible alignments between them and the observed sequence. The priors on the emission parameters is how we're going to encode the inductive bias, and that's what I'm going to explain now. So as I said before, people often associate characters through some kind of out of context prototypical pronunciation, and we don't really know how it works, so we don't really know how to operationalize it. But there is a resource that encodes this kind of out of context phonetic association already. That's phonetic keyboard layouts. So we don't need to think of how to define this association. We can just read character mappings off of these keyboards. But there is a constraint here. So because there are keyboard layouts, every symbol must be mapped to one and only one key. So we're inevitably going to have spurious mappings, which I highlighted here in red. They can happen because the native alphabet is larger than 26 characters, or if there are phonemes in one language that are not in the other. Like Arabic does not have the sound P, so the letter P ends up being paired to a leftover character that it's not related to, from what I can tell. To make our visual priors, we take the mappings from the Unicode confusables list. So this list groups together characters that can be made indistinguishable in certain fonts. So originally it was created to combat script spoofing attacks. Like I can take a URL and replace some characters with identical looking Cyrillic ones, and you can't see any difference right now. But if I change to a different font, you can see that where the first link has P and E, the second has Cyrillic R and Y. So maybe you can't tell them apart in most fonts, but their Unicode representations are different. So clicking on these links will take you to different web pages, which is something that an attacker could exploit. So the confusables list was created to hacker-proof the fonts, basically. But this list is extremely restrictive because the symbols must be nearly identical to make the list. And of course, this is not going to capture the whole complexity of the visual substitutions. So we do get a fair number of Russian mappings here, but for Arabic and Kannada, we just get a couple each because these scripts are a lot less similar to Latin than Cyrillic is to Latin. So we're not going to have enough to compile visual similarity priors for Arabic and Kannada. So now we have pairs of mappings of similar characters, but now we need to turn them into probabilistic priors. So we parameterize our emission distributions as multinomials. So here I'm showing the matrix of emission parameters, and each row corresponds to a latent character and each column to an observed character. And then we can create a conjugate Dirichlet prior that encodes our preferred character mappings. Mathematically, this just boils down to increasing the values in the cells corresponding to pairs of similar characters every time we re-estimate the parameters. And we also have some visual mappings where one Cyrillic character is mapped to 2 Latin characters. So for those cases, we're going to just increase the values for each of the 2 characters separately. So as I've just shown, when with the parameter matrix, the emission probabilities, the cells in this matrix, are defined for just 1 input and 1 output character. But we have to handle those one-to-many or null alignments. So we're going to approximate them using insertions and deletions. So these correspond to an empty character epsilon on the latent and the observed sides, respectively. Our finite state model consists of 2 mate components. The first one is the transition model. That's a 6-gram character level language model of the native script. And the second part is the emission model. It needs to have arcs corresponding to every possible substitution, insertion, and deletion. This is the schematic representation of our emission FST. I'm going to skip over the details here, but if you'd like to know more, please check out the paper. I'll just say that each part through this FST corresponds to a pair of input and output sequences and an alignment between them. And I wanted to highlight that this transducer has a limit on delay. And delay is the difference between the number of insertions and the number of deletions at each time step. So this is easier to visualize if you think of the alignment matrix. So every path through this matrix corresponds to an alignment between the input and the output sequences. And capping the delay is the same as restricting the distance from the diagonal in the alignment matrix. So now we're only summing over paths that fall entirely into this highlighted band that I'm showing here. So we use EM algorithm for training, where each step is just shortest distance computation in the expectation semmering. Expectation semmering is very cool mathematically. So when you do EM, you need to compute the sufficient statistics. In our case, it's the expected number of times, each Cyrillic character is substituted with each Latin one. But the cool thing about expectation semmering is that when you run the shortest distance algorithm, you get those statistics computed for free. So you don't need to think of how to do all the bookkeeping. And then the M step is just normalizing the counts. So this is all very elegant mathematically and maybe saves you time when you're writing code, but running it ends up being really slow. So we do end up needing a lot of tricks to speed up our training. So we use stepwise stochastic training where we update the parameters after processing each batch of sequences. We do curriculum learning where we train on the shortest sequences first. And while we train on the shorter sequences, we also prune emission arcs to make the model sparser. And we gradually increase the order of the language model in the transition transducer. So this all ended up being quite a lot of work. I don't mean to discourage anyone from using mathematically elegant solutions, but this is kind of a cautionary tale about considering the efficiency of those methods as well. All right, and the inference then is just, again, running the shortest path algorithm, just in a different semmering. FSTs are cool. So now let me introduce our data. So for Arabic, we use the LDC Bolt dataset, which consists of SMS and chat dialogues between Egyptian Arabic speakers. The messages are written in Romanized Arabic or Arabizi, and then they're manually transcribed into a standard called coda, or conventional orthography for dialectal Arabic. For Kannada, we use the Dakshina dataset. And unlike Arabic, here the texts are originally in the Kannada script, and they're taken from the Kannada Wikipedia. And the romanizations of the sentences are elicited from native speakers. And for Russian, we collect and partially annotate our own dataset. So we scrape the Romanized texts from the social network, vk.com. And for the native script side, we use a portion of the Taiga corpus, which is also collected from the same platform. And although, the two halves of our corpus come from the same website, the Taiga data looks like it's mostly from political discussion groups. So the vocabulary is very skewed compared to what our Romanized data has. So to collect the Romanized Russian data, we use the romanizations of common word as queries, as Karim Darvish has done for Arabizi. And I took a list of most common Russian words, and for each word, I generated all the possible romanizations I could think of, and then we use them as search queries. So that way we're getting a diverse set of user preferences in the data. Then I manually removed the sentences that weren't in Russian because the query romanizations sometimes happen to be identical to words in other languages, like in Polish. So Polish you can maybe remove with some kind of automatic language ID, but I also saw some search results in Romanized Ukrainian. I don't think language ID can do that, so you really need a native speaker when you're collecting this kind of data. Then the validation and test portions of the data are manually annotated by two native speakers. The training portions we don't annotate because we're doing an unsupervised approach. So the annotators remove all the foreign words or all the other words for which they don't have a standard Cyrillic spelling in mind. And here we show this part in red. And the annotators manually transcribe the rest of the sequence and correct what they perceive as minor misspellings, like hyphenation here in blue. And this is kind of a sensitive matter. It's a creative phenomenon, so you want to preserve the author's creative intent, but it's just not clear when and how to do it. Like, how would you introduce an equivalent misspelling in the output? Or how do I tell if the author did this intentionally or it's just a typo? And of course, the annotator is always limited by their own dialect. So I was one of the annotators, and very likely I could not recognize and preserve some dialectal variation in texts that were written by people from other countries or from other areas of Russia. All right, so now let's look at some results. So this graph shows character error rate, so lower is better. And the FST without informative priors does not perform particularly well. But with the visual prior, we already have a big improvement for Russian. For Arabic, we don't have a visual prior because we didn't have enough mappings there. A phonetic prior works even better because people generally use phonetic substitutions more than visual ones. And combining the phonetic and the visual ones gets the best results. So now we compare this to the performance of a supervised version of the same model, which we train on the annotated development data. It's just a few hundred sequences. And we see that we've actually come pretty close by adding this combined prior. So the informative priors do help to close this gap between supervision and no supervision. And we also compare to two handcrafted decoders available online, and they're actually doing even better than our supervised model, not really surprising. So if we look at what kind of errors our FST model makes, they're mostly character level noise, and usually they're caused by failure to disambiguate between two plausible decodings. And these graphs show fragments of confusion matrices for Arabic and for Russian. And here's an example of the FST decoding a character based on visual similarity when the author was actually using a phonetic substitution. Another type of error is inability to handle digraphs. Like instead of decoding SH into one character, it decodes S and H separately. This is probably due to a weak N-gram language model, because we'd expect that the N-gram language model would downweight unlikely native script bigrams. And some of the confusion, as expected, is caused by the noise in priors. Like here, the model incorrectly deciphers Latin X as the Russian soft sign. And it's happening because they got randomly mapped to the same key in one of our phonetic keyboard layouts, although they don't actually have any phonetic correspondence. So we've seen both the good and the bad sides of the finite state model. It's structured, which makes it easy to encode constraints and inductive biases, and also makes it more interpretable. They can learn from relatively small data, and they can perform exact maximization. But both training and inference take a lot of time. And as I mentioned, the N-gram character language model is weak. So an alternative would be a neural sequence to sequence model, which is less structured but more powerful. An RNN language model would be much stronger and we can also do inference much faster, but compared to an FST, it needs more training data. And also it can't do exact maximization, so it's prone to search errors. We're going to compare their performance on the decipherment task. And I wanted to again emphasize that we're training them both unsupervised, without parallel data. So most of the intuitions that I'm listing here on the slide come from previous studies done on supervised tasks, which are generally much more common in NLP. So that's just something I'd like you to keep in mind while you're looking at the results. So our sequence to sequence model is the unsupervised neural machine translation model, or UNMT, of Lampel et al. And it maps both the source and the target sequences into a latent space. And it's trained to denoise and reconstruct sentences in the same domain, perform back translation by going through the latent space, and discriminate between sentences from different domains. We're using the probabilistic formulation of the same approach introduced by Junchin He and colleagues. So here it's shown as translating between two domains. So in our case, one domain is the Romanized text and the other one is the native script text. We're also going to compare some model combinations. So the easiest way to combine two separately trained models is re-ranking. So we have one model generating its top K list of most likely candidates, and then the other model scores them and chooses the best one. Our second approach is product of experts. Here we perform beam search on the FST lattice, and each possible next output symbol is re-weighted by its probability under the seek-to-seek model at the corresponding time step. So this is a bit more complicated than regular weighted beam search because the definition of transitions is different under the two models. So FST processes the input and the output at the same time. So deletion of an input character corresponds to a transition under the FST, but it doesn't correspond to anything under the seek-to-seek. So we also have to use a special way of grouping the hypothesis on the beam. And we do that by the input length that's consumed so far in the FST. And as I said, we trained the two models separately and we combined them at test time. So now let's see the results for the two base models. And I wanted to first show the disclaimer and say that this isn't some kind of an abstract fair comparison of the unsupervised FST and the unsupervised seek-to-seek. They're trained on different amounts of data because the FST was too slow to train on all the data that was available. And the seek-to-seek just didn't work if we only trained it on the data, just the data that we gave to the FST. So we're just doing these experiments to get some applied insight on how one can combine these models, in finite time. So this graph shows character error rates, so lower is better. And our character level FST is doing better for all three languages, again, despite having less training data. And this is the character error rate for the model combinations. They have different levels of effectiveness, but mostly they're just kind of in between the scores of the two base models. So instead of bringing their strengths together to cover their different weak spots, They just kind of interpolate between the behaviors of the two base models. Re-ranked FST actually does a tiny bit better than the base FST, and product of experts also helps a little bit in one case. So here we're showing word error rate. Again, lower is better. And here we have the opposite picture. So unsupervised seek-to-seek is better than FST on word level, except for Canada for some reason. Model combinations are again scoring mostly in between. And again, re-ranking either helps a little or at least doesn't make things worse. And this is our final word level metric, blue. Here, higher is better. And again, the observations are similar to what we saw for word level error rate. Unsupervised seek-to-seek does better than unsupervised FST for Arabic and Russian, but not for Canada. And again, re-ranking occasionally helps a little bit. So now let's look at the actual outputs. And I'm going to use Russian here for the illustrative examples because I can actually read it. And we've seen quantitatively that for Russian, the FST does better on character level and seek-to-seek does better on word level. So this is what it actually looks like. So the FST typically predicts the right words, but with some character level corruption. So you can see there's a little bit of red in almost every word here. And the unsupervised seek-to-seek is good at reconstructing whole words, but it gets derailed into hallucinating, entirely unrelated fragments until it finally comes back on track. And re-ranking the seek-to-seek with the FST actually gets rid of the hallucination, and the output is almost fully correct. So the parts highlighted here in yellow aren't really errors. They're discrepancies with the gold annotation that are caused by the manual corrections that we introduced during annotation. So it's actually being faithful to the input. It's just going to get penalized for not performing spelling and grammar correction at the same time. So I'll just summarize our error analysis with a few high-level takeaways. So first of all, model combinations still suffer from search issues. We know that seek-to-seek models have search issues, like they delete or hallucinate words, they go into repetitions, or sometimes they produce empty outputs. And model combinations can help with some of these, but not as well as we hoped, which is why their scores are kind of in between the two base models. So at least for re-ranking, from what we can tell, the issue is with beam search. So something we've frequently observed is that the same hallucination makes its way to all the hypotheses in the final beam. And let me illustrate this with an example. So here I'm showing the Romanized input, the Cyrillic output, and the rough English translation of the sentence. And below there are top 5 final hypotheses that the unsupervised neural model generated from this input and their scores according to the re-ranker. So what's happening here? The seek-to-seek hallucinates something early in the sentence, I highlighted here in red, because the language model just gets immediately distracted by the first character in the input. So instead of the word this, which was expected, it predicts United Russia. That's the name of a political party, and it has absolutely nothing to do with the rest of the sentence. So then the seek-to-seek comes back on track and predicts the rest correctly for as long as we allow it to go on. But that's not good enough because, the re-ranker can't really do anything because the hallucination is everywhere in the beam and is just too far off. So either we need a much larger beam size or a diversity promoting search mechanism. So how did this become United Russia in the previous example? So if you remember what I said before, our Cyrillic data comes from political discussion groups. So names of political parties and politicians are disproportionately common on the native script side. So the seek-to-seek language model gets distracted by the first character in the Romanized sequence, and it just goes on to generate what it memorized. So in fact, 25% of the most common word level errors under the seek-to-seek are of this type, compared to just 3% for the FST. And finally, the FST errors are more repetitive. So here you can see the most populated fragments of the character level confusion matrices for the two base models. And you can see that the left one corresponding to the FST is notably sparser. And if you look more closely, for example, at this row here, you can see that instead of the letter ya, the FST most often predicts a, and the other substitutions are rare compared to that. But for the seek to seek, the error distribution for ya is much flatter, much closer to uniform, although the errors involving predicting relevant characters are a bit more likely than the rest. So because the errors of the finite state model are more repetitive, they might be easier to correct with some kind of rule-based post-processing. And now I just wanted to conclude with a few final thoughts. So first of all, the difference between languages really matter for this kind of cross-lingual research. So my idea of how informal romanization works was mostly shaped by what I saw in Russian, and not all of these intuitions apply to other languages. So one should really be mindful of how things like different writing systems influence how the phenomenon presents, or how, the script being less similar to Latin influences the amount of visual substitutions, for example. And in case of Canada, I had to go deep into the weeds of, how Unicode works for representing the Canada script. So even such seemingly technical difficulties, technical differences might really be important for what we encode in the model. And for my second point, I wanted to refer back to the annotation process. So it made me realize that transcribing non-standard language without the author in the loop is inevitably going to be lossy. So we corrected things that we thought of as errors, mainly because we didn't know how else to deal with them, because we don't know how the author would have spelled this word if they were writing in Cyrillic. But this means that we were standardizing creative language, at least to some extent. So we were losing the extra meaning that was encoded in the creative part. So it would have been much better if we could somehow combine the naturalness of social media with the participation aspect of crowdsourcing, but it's not really clear to me how to do something like that. And my final point is that I still believe that combining unsupervised FSTs and neural models could work. It's a promising direction for future work, and it could harness their complementary strength. We didn't really get that from our simple test time combinations, but we could try the same kind of joint decoding at training time so that the models can learn from each other. Or we could structurally integrate the desired properties of one model into the other, which is what most current research on neuralizing FSTs does. Or we could try and bias one of the models towards behaving like the other. And if someone in the audience has any intuitions about combining finite state and neural models, I'd love to hear them. And yeah, these are the thoughts that I wanted to open the discussion with. And thank you all for listening.
Thanks, Maria. I'll just clap on behalf of everyone, though some people are putting clap emojis. Also great. Yeah, we'll now be taking questions. Feel free to just unmute and ask, or ask on Dory, which has an anonymous option, in which case I'll read it out for you.
Right, so if I may start, thank you so much, Maria, for interesting presentation and interesting work. I have just two comments. So first, how you were saying, like for the Arabic, sometimes there was the issue of two, where you had one pronounced letter but written in two letters, such as the she, sha, s, and h. Have you tried normalizing this into a one symbol, which might work, or it might be an idea to work with?
Yeah, thank you. So this is actually something that, so in Russian, for example, you could have the digraph SH, where you have the S and H separately. I don't know if this, I wish I had a whiteboard. So you could have the bigram sh.
Yeah. So
s and h separately, and then it would be romanized as sh, but it's not supposed to be deciphered as sh. So we try to just not encode any explicit preference for this into our model.
Yeah.
And we were just hoping that it learns to disambiguate between sh and sh, but not really. Is this bigram uncommon, in Arabic?
You mean the two letters?
Yes.
Yeah, yes, I think this is uncommon. Yeah.
So we were
they could occur together, and I understand your point that this might be confusing because you wouldn't know that whether this is mapping for two distinct phonemes or just mapping one phoneme. Sure.
Yes.
Right.
So we were generally trying to sort of, the idea was that, what if we didn't know anything about the language, but we knew something about the characters, and we just encoded that information about the characters into the model.
Yeah.
And we were trying to not encode anything besides that. So we were just curious what our model can learn, and we were hoping that the language model will take care of this, but it did not.
Yeah. Okay. Right. Another one, please. So you know how it's an issue for Arabic, for example, where you have the character to character mapping, where you have one character to two characters or the other way around. So they are not equal in number of letters. So, I mean, it would be nice to look at the results specifically for these types of words, for the sequence to sequence, if it improved over the FST. I don't know if you've looked into these specific mappings, if it was better to use the sequence to sequence.
So this is a good question. We did not look specifically into this type of error where, is it better at deciphering a digraph correctly or not? But if we looked at generally at like the error patterns for, what was the CER per word? So it was, what we saw was that FST is more likely to have some noise in, almost every word, but seek-to-seek either gets the word completely right or it just doesn't get the word right at all, like maybe because it, hallucinated something instead of half of the sentence or just dropped a lot of it or something. So seek-to-seek was definitely much better at getting the full words correct. So I'm assuming this type of error it would also be better at, because the language model is much stronger.
Yeah, and the data set that you mentioned is, I think it's quite small. Maybe with a bigger data set would have a better results. So it might be an excellent approach anyway. Thank you.
Thank you.
I have a question.
Sure.
Have you noticed any effects of people who are romanizing to language to vocalize languages that are not English? So like sh being ch because that's how they do it in French.
Yeah, that's a great question too. That's definitely we did have some of that in Arabic, where people would use the French phonetics instead, like French instead of English as the intermediate language. So we didn't do anything special about that. I think it would be interesting to have a model that, considers, besides just, maybe taking into account whether the user prefers phonetic or visual, it also tries to identify which language the user relies on for the phonetics. And this is a thing in Russian too. So sometimes people use German as the intermediate language, although it's a lot less common than English. But yeah, we didn't do anything for that explicitly. And I think in most of our data, like in our data, English was more popular. But I think for Romanized version of other dialects, like we were working with Egyptian Arabic, but with Moroccan Arabic, it would have been a lot more of the French ones. Probably Taha would know better than I do.
Yeah, exactly. Like it depends on the person's other language, and this is where you have mixing with an English preference phonemes over the French preference phonemes. You see that more in Moroccan, Algerian countries where they have French as a second language. But if you want for a crazy case in Lebanon, they use both. So they use the SH and the CH because it depends on the people. Some of them, they have English or French as a second language. And this was mainly some of the mess that I was dealing with. Maybe I can present my work sometime soon.
Yeah, that sounds very interesting. Yeah, I mean, it was just, I guess, lucky that my data was relatively homogeneous in that sense. But I didn't have when I started this work, we didn't have a good data set of Arabizi for other dialects that was also fully transcribed. Maybe now there is one, I'm not sure.
It's very scarce. It's very, this is very informal, and it's mostly used in mobile texting. I mean, even when you want to collect something online from social media, you'd have to go through lots of filtering from other languages because it's code switched with English and mixed with English and French. Yeah.
Okay, thank you.
Anyway, yeah, thank you.
Any other questions?
Yeah, I'm just curious because Google Translate now. Hi, it's Boaz. I'm sorry, I cannot turn on my camera.
Oh, no worries.
Google Translate also supports Arabizi right now, right? And I think it does a pretty good job of transliteration from different languages. So I'm curious, what's your take on that? How does it compare to what you're doing? Thank you. And thank you for the talk.
Oh, thanks. Yeah, I mean, I think in practice, okay, let me get to the results here. I don't think there is any point in using our system in practice, honestly. Like, why would you use, in general, why would you use an unsupervised system when you can use a supervised one, when you can just have someone sit down and annotate a few hundred sequences and it already works better? And here, if you look at the gray bars, the handcrafted ones, for both languages, they work better. So here for Arabic, we didn't use the Google Translate, we used something called Yamli, which is probably even better. And, if you can just have I'm not really sure what's inside Yamli, but for Russian, it's just someone just sat down and wrote a bunch of rules, and it already works better than than whatever models we were trying to train. So it's if you're considering which model to use in practice for deciphering this kind of transliteration, it's just much easier to just get a native speaker who will write out a bunch of rules and then it will work. Or, worst case, they annotate some sequences and then it's better than what we tried here. So we were mainly interested in, what can our model learn if we don't give it any supervision, but just give it this feedback? Is it enough? Is it enough for a computational model to decipher the Romanized text if it just has a language model of the original script and some information about what characters have something in common? Okay, I hope that made sense.
Yeah, great, thank you.
So yes, my answer is I'm sure Google does better than what we did here.
Yeah, if I may add to this, we've tried transliterating Arabizi and over Google. So the difference with Yamli is that it is online, it is word by word, and for every word you have a list of words that you can choose the correct transliteration. But the system in Google, it transliterates the whole sentence automatically. And for purely dialectal words, it was horrible. It was very bad transliterations. Yeah, I think, and it makes sense because the same word could be transliterated to different words depending on the dialect. And for Google, they didn't give you the option to specify a dialect. They're just trying to make it generic. So yeah.
So when I was using Yamli was, it does give you options word by word, but I just needed to transliterate the entire text. So I just went with the first option that it suggested for each of the words. So I just did it, the way that someone who does not speak Arabic would have done it. And it still worked better than, anything else than we've tried for Arabic.
I've tried this as well before, but Did you type them word by word? Because you could, if you paste the text, it doesn't give you a transliteration. So were you typing them?
I think I pasted them word by word. So
Okay.
I couldn't paste it. No, I pasted the whole sentence and then I clicked on every word separately.
Yeah.
So that was the, yeah, I mean, it's not designed for this.
Yeah, exactly. For that, I used a trick. There are some programs that are auto typer, and you give them a passage and then they type them, and it worked with the Emily.
Oh,
I mean,
that's nice.
it saved me a lot of time. Yeah.
Thank you. Yeah, I just had to I had 1,000 sentences in my test set, and I had to just click on every word in every sentence and select the first option. That took quite a lot of time.
Yeah, it's some of the some of the work that we go through as PhD in this discipline is the lots of manual stuff that we have to do them by hand, and unfortunately, there's no one else to do them for us. So, yeah, I know exactly what you've been through.
Thank you.
I've tried also an auto clicker sometimes when you just need to click the one best, have something that clicks in the same spot on the screen.
That's a great idea.
One question, it's wonderful to use rules when we can make them, but obviously people are so creative. There are always going to be things that weren't necessarily available to annotate or something when, trying to extend. Do you know, perhaps for the Russian, if there are any situations where the unsupervised approach might be slightly complementary, either because the supervision didn't see certain examples or something like this, or maybe they focus on different things?
Yeah, I think that's a great question. So we did have some really creative people in our Russian dataset who used, patterns that we have not seen before. And even for me as an annotator, it was challenging to, decipher what they were saying. So unfortunately, we did not have any kind of user-specific parameterization. So what we did was we just kind of encoded the similarities. Basically, the model was kind of trying to use the majority patterns because it had the same parameters for all the sentences. So for those really creative ones, our unsupervised model also did not do well. So it mostly just produced garbage. But I think if we could have some kind of user-specific parameters where it tries to fit to the preferences of a specific user, and just using the same kind of information about character similarity in a special way for every person, then I think that could have worked. I think that would have been nice. But also we have the way we use the way we define the similarities between characters is quite restrictive. And for example, there's I had it somewhere in the beginning. So this person who used the creative spellings did so you can see here the Cyrillic L substituted by a V, because it kind of looks like an upside down V when it's written in some fonts. And this is what this person did. And it's just not in the, Unicode confusables list or anything. So it would also require a different, probably a much more nuanced definition of similarity.
Yeah, and I guess I should say as well, these were excellent slides. All of the examples were really nice. So thank you very much for that.
Thank you. Yeah, I got a message that someone else has a question.
Yeah, hi, Johan. Thanks for the talk. I was just wondering, I mean, I found this interesting, this attempt to combine the both models and use kind of the language model information from the sequence to sequence model to correct things. But you pointed out that this model is quite limited and it was kind of biased from the source it was trained on, as far as I had understood, right? But I was wondering, so because I was in the opposite situation myself when I was trying to understand English written in the Korean script, right? So, which Korean people do a lot of the time. And when I did this, I found that I just, I realized some of the things, but then the final insight came from the whole sentence making sense, right? So I was wondering, I mean, I don't actually know what's on the market right now, but there should probably be good language model based spell checkers where you can spell check a whole sentence, right? So if you just run such an out of the box spell checker on whatever your character based model creates, which would be some stuff with spelling errors, what would the result be? Have you tried this or ever thought of trying this?
Yeah, I think that's really interesting. So there's a bit of a difference that we're decoding not into English, we're decoding into Russian or Arabic or Kannada. And I bet that the spell checkers available for those languages are not as good as you would find for English. So it would probably still be relying on individual words. And for Arabic especially, the problem is that, we're using dialectal Arabic, which does not have a conventional orthography. So we use this artificial standard, and I don't know how the, Arabic spell checkers would work with that. But I think the idea is very interesting, and probably just some rules on top of the FST could work. But
I was just thinking that you could easily train a much larger and better language model on just a huge corpus unsupervised instead of needing the sequence-to-sequence model supervised, right?
Yeah, I think so. Yes, I think that could work. That's a really cool idea. The only other thing that, what I can tell from observing the Russian data, so we scraped it from social media, and it had a lot of words that, I have never seen before. It had a lot of slang. It had a lot of, proper names that were, a lot of the people were talking about gaming. So they were using proper names that I've never heard of, and slang words that specific to their community. So I'm worried that spell checkers would just, again, think that this is all noise and this all needs to be, transformed into something that there is in the dictionary. But yeah, I guess it depends on the domain of the data.
Yeah, interesting point. Yeah, I mean, what to do in that case? It's all bets are off anyway. If people are talking about something nobody knows, nobody else knows.
Yeah, we did end up when we were annotating the Russian data, we did end up dropping a bunch of those words because, like I said, anything that we didn't know how to spell in Cyrillic or we weren't sure, we had to discard because, how would we annotate that? So a lot of those gaming words we just had to forego.
Yeah, I was just thinking, I mean, if you're not yourself a gamer, then maybe even if you're native Russian, it must be hard to understand what they're talking about.
Yeah, I mean, I think I guessed some of the slang. So the proper names, there's just no way. The slang words that kind of looked like they were Russian, and I could see that maybe these are borrowing from English that are adapted to look like Russian a little bit. Those I could figure out, so I just did my best guess, but I don't know if that was correct. So it could very well be just, just wrong.
Interesting. Thank you.
Thank you.
Thanks. And if there are no more questions, we're ending right on time, which is great. Yeah, thank you so much, Maria, for joining us, and to everyone else. In 2 weeks, we'll have Alain Surge, and that's going to be a great talk as well. So see you then.
Thank you for having me, and thank you everyone for attending and the great questions.
Thank you.